Yeah. Yeah. Yesterday. Sure. All right, here, folks. We got one more section to get through here in chapter 3. Let's stop talking, please. This one last section of chapter 3, we're going to talk about the tangent function. All the techniques we're going to use are going to be the same techniques that we did in 3.1, just with some minor modifications because the function is a little bit different. But by and large, same ideas, same steps, same techniques. So it should be, if you felt comfortable with the previous stuff, this should be pretty straightforward. So we're going to start by talking about the tangent function. So in general, when we talk about the tangent function, we notice that a lot of this is going to be the same as sine and cosine, right? But there's some obvious differences right away. So for sine and cosine, the domain was all real numbers. For tangent, that's not the case, right? We're seeing that tangent is going to be undefined every odd multiple of pi over 2. So at pi over 2, it's undefined. At 3 pi over 2, it's undefined. At 5 pi over 2, undefined. 7 pi over 2, undefined, etc., etc., etc. The same thing would go with the negatives. So at negative pi over 2, negative 3 pi over 2, negative 5 pi over 2, negative 7 pi over 2, etc., all undefined. Okay, well, that's a little bit different, but okay. We'll talk about what that looks like in a moment. The range is all real numbers. Instead of being stuck bounded between -1 and +1 like sine and cosine were, tangent is unbounded, so it has no minimum value or maximum value because the graph is going to be, have an arrow pointing down and arrow pointing up on it. Well, sine had odd symmetry, so that's not a big deal. And all of these trig functions have been continuous over their entire domain. The midline was y equals 0 for both sine and cosine. But the period for sine and cosine was 2 pi. Here we see that the period for tangent is just 1 pi. And the frequency, just like sine and cosine, is 1 over the period. So that looks different, but it's really kind of the same idea. So for our general version of tangent, the midline, still y equals k. The period is going to just be pi times the absolute value of c. And the frequency is 1 over pi times the absolute value of c. What do you notice that we always talk about for sine and cosine, but we don't list for tangent? Well, the frequency is different, but there's something that we talk about for sine and cosine that we don't even mention here for tangent. Amplitude, very good. And the reason we don't mention an amplitude here is because tangent doesn't have an amplitude because it doesn't have a maximum or minimum value, right? Because the range is all real numbers. There's not like a maximum or minimum value to tangent, so there will be no amplitude for a tangent function. So let's go ahead and graph tangent just to kind of see what it looks like. So if I go to graph tangent, I'm going to go to my reference points sheet that I gave you guys earlier in this chapter. I'm going to go down to my tangent points, and those are going to be the values that I'm going to be graphing. So at negative pi over 2, tangent is undefined. At negative pi over 4, the y-coordinate's negative 1. At 0, the y is 0. At pi over 4, the y is 1. At pi over 2, we're undefined again. So when we're graphing at pi over 2 and negative pi over 2, when the graph is undefined, that's going to create we're going to draw a vertical asymptote to represent that. And then at negative pi over 4, it was negative 1. At 0, we were 0. And at positive pi over 4, we're positive 1. So when I connect our graph, it kind of looks like that. Everybody's okay with that? So if I want to extend this graph to fill the space, looks like every other tick mark should be an asymptote. So I like to draw those in first. And then in the middle is going to be the value that's on the x-axis. In between that value and the asymptote to the left, we're at negative 1. And in between that middle value and the asymptote on the right, we're at positive 1. And we'll just kind of draw. And now I'm just going to go ahead and fill in everything that I have left. So that's our graph of regular old tangent. So let's say that we wanted to graph the following. Yes, Reese. Why did it go up but not down? Well, I just drew like to 3 pi, right? Like I just pretended like I had, just to practice extending it. So I just, where the graph ended, I just said, okay, I'm done drawing. Obviously it keeps going, but like if I just keep going, I'm never going to stop because it goes on forever. I have to just eventually just say like, we're done, because I've ran out of paper. In this case, it's just like, that's the end of what I drew. Is that okay? So there's no rhyme or reason. It just was like, it's there. So let's do another one of these equation to graph problems. So let's say we want to graph tan of 2x minus 1. So just like all of our other graphing problems that we've talked about, I want to start by writing down the values for A, C, H, and K. So to do that, can we do that without rewriting this tangent thing? What do you guys think? Can you look at the equation, just say the values for A, C, H, and K? Let's try it. What's A?
0.
Is it 1 or is it 0? 1 is correct because it's multiplied, right? If it's not there, but the A is like multiplied in the problem, I know not there with multiplication means 1. What's the C going to be? Not 2. 1/2, 1 over 2. Because what we're seeing here is that 2 is 1 over C. So C is going to be 1 over 2. What's H going to be? 0. Notice that H is being subtracted. If you don't see subtraction, then you must have been subtracting by 0, because subtracting by 0 is like doing nothing at all, right? Just like multiplying by 1 is like doing nothing at all. And the K is -1. So just like before, I'm going to write my transformation map. So I have CX plus H, AY plus K. And then I'm going to take those key points from my reference sheet. So again, these I'm just pulling from that reference points sheet. You would look these up or be provided or have them provided to you. I, being a math teacher and done this job for 15 years and done literally thousands of these kinds of problems, have been memorized for some time, but that's not an expectation for you. And now, just like all of our previous graphing problems, I'm just going to plug these x's and y's into my map to get my new points that I'll be plotting. So when I plug -pi over 2 in for x, what do we get? I have 1/2 times -pi over 2. When we multiply fractions, we multiply tops together and bottoms together. So 1 times pi is pi, and 2 times 2 is, so this should be -pi over 4 plus 0, which is just -pi over 4. What do I get when I do 1 times undefined minus 1? Well, for our purposes, whatever you do at undefined just stays undefined, right? You multiply it by a non-zero constant, add anything you want or subtract anything you want from it, it's still staying undefined. Because it's kind of like an infinity, right? If I add 3 to infinity, how much do I have? Still infinity, man. It's just still the same. You know what I'm saying? Okay. If I plug in -pi over 4 for x, what do I get? -pi over 8. And then 1 times -1 minus 1 is -2. If I plug 0 in for x and 0 in for y, well, that's easy. That's just going to be 0, -1. If I plug pi over positive pi over 4 in, I'm going to get positive pi over 8. If I plug 1 in for y, I have 1 times 1 minus 1, which is 0. And then if I do the last one, if I plug in positive pi over 2, that should give me positive pi over 4. And undefineds always stay undefined. So let's draw this graph, and maybe I'll put it on a scale from negative 2 pi to positive 2 pi. And I'll go by quarters here, I guess. 4, 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay. So let's start by graphing. I have negative pi over 4 undefined. I like to draw my asymptotes in first. I have positive pi over 4 undefined. Then I have 0, negative 1. Then I have negative pi over 8, negative 2. So that's going to be here, halfway in between negative pi over 4 and 0. And I have positive pi over 8, 0. That's going to be halfway between 0 and positive pi over 4. Because I know an 8 is half of a fourth. Those of you that are cookers might know that. If you're handy in the kitchen, you've probably used enough cups and teaspoons and measuring tools to know that. If you haven't spent any time in the kitchen, give it a try. Cooking can be fun. So I'm just going to go ahead and draw in all my other asymptotes to fill the space. So I'm not going to calculate any more points. I'm just going to kind of follow the pattern from the one period of my tangent function that I've drawn and just kind of continue that through. So if I follow the same pattern, I'm just going to kind of do this. Is everybody okay with what I mean by just following the same pattern? I'll take it from your silence when I ask that question, you mean yes, that you're totally okay with it. If you're not, you should speak up, because I can do more, but if you don't say anything, I assume that it's okay with what we're doing. But if you're confused, like, let me know, and I can say more or go over a detail again, or we can backtrack to where you weren't confused and try to fill in whatever the missing piece is for you. Reese? I'm just redrawing that same shape. Yep. So I'm just keeping the same spacing between asymptotes and drawing the same thing in between each asymptote, and it just repeating over and over and over again till I'm usually pretty bored by the end of it, but it's not difficult, right? We're just copying it again and again and again just to fill the space provided. I was pretending like, you know, like you got on your homework quiz sheet where you had a space to put the graph in, then you need to fill whatever else is there. Same idea here. Does that feel okay? Does this feel any really different than the previous things? It's like almost the exact same thing, just like when you draw your graph, instead of it looking like a wave, it now looks like this. But like the way we get the points to plot, exactly the same. The way we extend the graph, exactly the same. The way we pull our values for ACH and K, exactly the same. The way we write our function map to get our new points, exactly the same. We're just using different points and your end product looks a little different, but the process is exactly the same, right? This is why I like teaching this way with this process, is because, well, it just now like exactly every problem is basically exactly the same, right? The technique just is, we're doing the same thing every time. Let's do some examples of going from graph to equation. Right? When I do this process, it's going to be almost the same. There's just going to be a couple of little details that are going to be a little bit different. So let's say we're looking at this graph of a tangent function. So I'm looking for the values for A, C, H, and K so that I can fill those into my equation, and then I'm done, right? If I went back to the beginning, I know that the midline is still K, so let's find that first. If I were to look at what horizontal line is going to divide this graph in half, it appears to be this one right here. Do you guys agree with that?
Sure.
Where it's like right at where the graph is bending, right? At this spot, we go from like bending, down to like bending up. So that's going to be where our midline is going to lie. So our K value should be 2. So far, so good. The next thing we're going to do is look for our A. So when we did this for sine or cosine, we looked for the amplitude to figure out our A. Now, the graph of tangent doesn't have an amplitude, but what I'm going to do is I'm just going to look for the distance from that other given point, and it doesn't matter which one you picked. Actually, let's draw it here. Those are going to give us our absolute value of A. So if I'm going from 2, say, up to 5, how far did we go? 3, which would tell us that A is then plus or minus 3. So far, so good. I know that from asymptote to asymptote is 1 period. So if we went from negative pi to 0, how far was that? 1 pi, right? Now, this is one of the few things that are different. Remember, if we go back to the beginning, we said that for tangent, 1 period is pi times the absolute value of c as opposed to 2 pi. So if pi times the absolute value of c has to equal pi, what does c got to be? Just 1, and remember we always choose c to be positive. So the last thing I need to do is we need to find whether a should be positive or negative and our value for h. I'm going to do that the exact same way we've done before. So I'm going to pick a point from the parent function of tangent. I'm going to use the point 0, 0 because I want the point whose x-coordinate is 0. If I go back to the parent function of tangent, we drew that right here. There's 0, 0. Before 0, 0, which is a midline point, the graph points down, and then after 0, 0, the graph points up. So that's the type of midline point I have, is like a down midline point up. If I go to my resultant function, I'm going to pick a midline point. I'm going to pick this one right here because, well, the coordinate is labeled for me, so I don't have to think too much about it. If I look at this midline point, before that midline point, the graph points up, and after that midline point, the graph points down. So since these are the opposite types of midline points, what can I say? I know the A is negative. And then since the x-coordinate of my parent function is a 0, the x-coordinate of my resultant function is my h. Bless you. And now we have everything we need. We're just filling in our blanks. The x-coordinate of my parent function is 0. So the x-coordinate of my resultant function is h. So the x-coordinate of my resultant function is at negative pi over 2. Hey, Polly, will you grab the door for me? Will you grab the door? Thanks.
Yeah.
Should we do one more? Okay. Okay. What do we start by finding? Let's find k first. Look at the graph and tell me what k is. Look at the picture that I've given to you and see if you can tell me what k is. Reese? -1. I agree. So this appears to be my midline. So far, so good. Now take a look at the picture and see if you can tell me what the absolute value of A is. What is the absolute value of A going to be? Reese? 1. Good. So again, we're just looking at that distance there. And since it's the absolute value of A is 1, the A itself has to be plus or minus 1. Now let's find the C. What do we need to look at to find the C? Ava? Great, which is the period. Yup. And this looks like it goes from negative pi over 4 to positive pi over 4. How far is that? Reese? it's pi over 2, right? Because it's a quarter pi plus a quarter pi. 2 quarters makes a half. And then for tangent, how do I calculate the period? What's my formula? Someone other than Reese, who is doing a wonderful job, and I appreciate her volunteering. Ava. Excellent. So if I know pi times the absolute value of c has to equal pi over 2, what does just c have to be? Ava.
2.
Close. Because 2 times pi would be 2 pi, right? 1 over 2, yes. So pi times a half should be pi over 2. And we're always going to choose c to be positive. Now the last piece is to figure out the sign for a and the value for h. To do that, we're going to pick a point from our parent function. What point do we always pick from our parent function when we're writing a tangent? It's the point 0, 0. We're going to do that every single time we write a tangent function. What type of point is a tangent function? It's always pointing down, midline, pointing up. Yes, certainly. So from our resultant function that we're given, which point should we pick? 0, -1. I want that point on the midline. Very good. And I'm going to use that one as opposed to like this one, or this one, because it's labeled for me. I don't have to figure out what the coordinates are. If they're telling me what the coordinates are, I'll take it. One less thing for me to screw up, right? Now, what type of midline point is that? Before 0, -1, the graph points down. And after 0, -1, it points up. So if I compare those type of point, what can I say? A is positive. Whoa, Boise. Because they're the same. That's excellent. And then if I compare their x coordinates, what can I say about h? Zero. That's correct. So if we put this all together then, we can say y equals a times tan of 1 over c. I'm just going to write it as the reciprocal though, since c was a fraction. X minus h plus k. Instead of writing plus a -1, I just wrote -1. Now if you wanted to write that as just tan 2x minus 1, that's okay. What do you guys think on this? It's okay, right? It's the same process as before. There's a couple of minor modifications because, the graph of tangent doesn't have an asymptote. And its period is a little different, but like, oh my goodness, it's like remarkably the same process, right? All right. So let's look at what we have so far. So last week, there was a Delta Math assignment, and we assigned problems 1 through 14. That's going on to this Sunday's problem set. Today, I'm going to assign 15 to 26. I'm going to assign worksheet 4, but I'm only going to assign you guys to do 2, 6, and 8 from that. I want to double check that to make sure I've written down the right numbers. I put an X through everything I didn't want you to do. So it should be really obvious which ones to do. Yep. And then on worksheet 5, I want you to do numbers 5 and 7. Again, I put X's through everything I didn't want you to do, so it should be really obvious. It's 4, 5, 5, and 7. Okay. Friday, we'll assign the review and your note card. And then the following Tuesday, right? No, what's today? Tuesday. Okay. So this, I meant here Thursday then, right? And then this I meant Monday. What's going on? I know, I heard you mumble something. Go ahead, what was it?
No, I just 3 tests now.
Okay, well, I don't care on the date that we do this test. If it makes life more convenient, I will start the next chapter on Monday and we can take the test on Wednesday. If that makes life easier, I'm happy to do that. All you have to do is ask.
Okay, Tuesday. So let's Monday. Okay, fine. Yeah, Monday.
Are you sure?
Yeah.
Okay.
No,
I just want you, like, that's perfectly reasonable request. I'm happy to do that. If you want me to move it. Okay. Okay. If you change your mind, we can talk about it again on Friday or Thursday.
Okay.
You know, if we change our minds and you're like, oh boy, I think Monday got worse all of a sudden, it's okay.
That's good.
So at this point, I am done for today. I would suggest either working on your Delta Math if you haven't finished that, starting one of these homework assignments if you haven't started one of those, or if you've started one and you haven't finished a piece of it, or you can start putting together your note card. In particular, when you're building your note card, we've talked about 3 kinds of problems, right? Equation to graph, graph to equation, or description to equation, right? Those are the 3 types of problems we've dealt with in chapter 3. That's how I would organize my note card. I would have, like, what are the things I need to go from a graph or from equation to graph? What are the formulas that I use to do that? What is the process? Give myself an example, maybe with the equations in real time and how I'm plugging, and just notes to myself of like how I need to plug things in, or what are the things that I need to watch out for that have screwed me up when I did the homework or when I'm working on the review. Then I would have graph to equation, and I'd have what are the formulas I use to do that, or the facts that I use to do that. Included maybe in an example where I'm using those formulas in context to remind myself like where these letters are coming from or whatever. And then I'd have, description to equation and write down some of the formulas I use there, some of the facts that I use to do that. Does that make sense to you guys? This test very much is how good is your note card? If your note card is good and you have everything you need organized in a way that's like sensible, this should be very easy to do well. If you don't have a good note card or a note card at all, there was a lot of memorization on here that's going to come up and bite you. And there's a lot of like little details that if you don't have a little note about it to remind yourself, like how easy is it to screw up the value for C or the value for h when you're doing your partner assignment the other day, right? Very easy to make a mistake on that when you're graphing. If you do that, you get a bunch of stuff wrong because of it. You know what I'm saying? So just, you want to be careful. If you do things right, you usually do it mega right and get lots of stuff correct. If you do a bunch of little stuff wrong, you can get a lot of stuff after it wrong because of follow through. Okay, so just be careful on that. Again, I would make notes to myself on my note card about places where like I've made a mistake. You know, it's very easy to write down negative h instead of positive h, right? It's really easy to write down 1 over c instead of c. You know, and if you do that, you get all your points wrong. Because if you do that, it's all there is to it, right? Now, I tried to write a test in which you're not punished too harshly for those kind of mistakes. I tried to arrange my questions so that, you know, I evaluate those things as separate skills. But like, let's try to make sure we get that kind of stuff right? It's easy to make a mistake on. You can make a note to yourself on your note card with an example, you know, and you should be able to do really, really well here, okay? But you got to have a well-designed note card, okay? I'm done talking for today.